Hello students, in previous lecture we have seen the theorem every permutation sigma of finite set is a product of disjoint cycle, and we have seen some examples. Now in this lecture we will see one more example and then move towards transposition. Let's see this example. Consider permutation sigma has total 6 symbols. 1 goes to 6, 2 goes to 5, 3 goes to 2, 4 goes to 4, 5 goes to 3, 6 goes to 1. So to find out product of disjoint cycles. So here first find out the orbit which contains more than one element. So first we will start from 1. So first 1 is moved to 6, 6 goes to 1. So orbit containing 1 has 2 elements, means cycle of length 2 which has 2 elements 1 and 6, right? So I will write directly sigma as 1 2 3 4 5 6 6 5 2 4 3 1, right? So write down the product of cycles. So 1 goes to 6, 1 goes to 6, 6 goes to 1. So here is complete first cycle. Next start from 2, 2 goes to 5, 5 goes to 3 and 3 goes to 2. 2 is already in our set. So this is second cycle whose length is 3. Next 4 is fixed and 5 is in our set. So this is the product of two disjoint cycles. So there is no common element between these two, and this product of cycle can be written in the form of again permutation. So and here this can be written as 116 into 2563. We have seen the note that here product of permutation multiplication is not commutative, but disjoint cycle is commutative. Here there are two disjoint cycle which can be written as 2 5 3 into 1 6. So order of permutation is not important here. The if we have two disjoint cycle, then it is commutative. So here two disjoint cycles, so this can be written like this or this can be written like this. So multiplication of disjoint cycle is commutative. So order of factors here 1 6 and 2 5 3 is not important. Now let's see another example. Consider the cycles. So 1 4 5 6 and 2 1 5 which belong to S6. Then find disjoint cycle. So these two cycles are not disjoint. So here 1 5 1 5 are the common. So then find disjoint cycle. So these are two cycles, so which belongs to S6. So here 1 4 5 6. So this is the cycle of length 4, right? And this is second cycle 2 1 5, right? So this is, I will write this as sigma, and I will write this as mu, which is 2 1 5 2 1 5, second cycle. So first cycle can be written in the permutation form. So sigma can be written as 1 4 5 6 can be written as, so here 1 2 3 4 5 6, total there are 6 symbols. So 1 to 6. Now this cycle can be written in the permutation. So 1 goes to 4. So this cycle like this. So 1 goes to 4, 4 goes to 5, 4 goes to 5 and 5 goes to 6, and last 6 goes to 1. Sorry, here 1 goes to 4, 4 goes to 5, 5 goes to 6 and 6 goes to 1. Here 2 and 3 are constant, means as it is fixed. So this is sigma. Now next mu 2 1 5. So total there are 6 symbols. So first write down 1 2 3 4 5 6. Next here what we have, 2 goes to 1, 2 goes to 1, 1 goes to 5, 2 goes to 1, 1 goes to 5, and 5 goes to 2, right? So 3, 4, 6 are fixed. Now to find out the product, so product of this sigma into tau is equal to, what will we get? So 1, 2, 3, 4, 5, 6. So 4, 2, 3, 5, 6, 1 into mu 1, 2, 3, 4, 5, 6, 5, 1, 3, 4, 2, 6. So total there are 6 symbols, 1, 2, 3, 4, 5, 6. So taking product, which is start from right hand side, 1 goes to 5, 5 goes to 6. Next for 2, 2 goes to 1, 1 goes to 4. Next for 3, 3 goes to 3, 3 goes to 3. Next for 4, 4 goes to 4, 4 goes to 5, 5, 5 goes to 2, 2 goes to 2. Next for 6, 6 goes to 6, 6 goes to 1. So this is permutation sigma tau. So this can be written as product of disjoint cycle. So the disjoint cycle is, so here to find out the disjoint cycle, so 1 goes to, so start from 1, 1 goes to 6, 1 goes to 6, 6 goes to 1. So we will stop here. Now next we will start next element. So we will start 2, 2 goes to 4, 2 goes to 4, 4 goes to 2 goes to 4, 4 goes to 5, 5 goes to 2, 2 is again already in the set. Now next is here 1, 2, 3 is constant, so there is no, we will not take it, this is the 3 is fixed. So 1, 2, 3, 4, 5, 6, so total 6 elements. So this is the product of disjoint cycle. There is no common element between these two cycles, so which is product of disjoint cycle, product of disjoint cycle, right? Let's see one more example. Compute the product of cycles, the product of cycles. So first 1, 4, 5, 7, 8, 2, 5, 7. So we have given 3 cycle which is not disjoint, because here 5 and here is 5, here 7, 7 means if we take any two, so there is no intersection is not empty. So this is not disjoint cycles. Now to find out the product of that cycles, this is first, second one is 1, 3, 2, 7, 4, 8, 6, which belongs to S8, is again belongs to S8. So to find out the product of cycles, for here, since here these cycles are not disjoint, since the cycles are not disjoint, right? So first I will write 1, 4, 5, 7, 8, 2, 5, 7. So first find out cycle into permutation. So total there are 8 elements, right? So here 1, 2, 3, 4, 5, 6, 7, 8. Now for first cycle I will write 1 goes to 4, 4 goes to 5, 5 goes to 1, 5 goes to 1. So other elements are as it is, 2 goes to 2, 3 goes to 3, 6 goes to 6, 7 goes to 7, 8 goes to 8. So this is permutation for cycle first. Now for second cycle we have to find second permutation. So here total there are 8 elements, 1, 2, 3, 4, 5, 6, 7, 8. So here 7 goes to 8 and 8 goes to 7. So other elements are same, 1, 2, 3, 4, 5, 6, and last this is again we have total which belongs to a set. So 1 2 3 4 5 6 7 8. So here 2 goes to 5, 2 goes to 5, 5 goes to 7, 5 goes to 7, and 7 goes to 2. So other element as it is 1 3 4. Here 6 goes to 6, 8 goes to 8. So the product will start from right hand side. So I will first write down all 8 elements 1 2 3 4 5 6 7 8. Now start from 1. So 1 goes to 1, 1 goes to 1. So here 1 goes to 1. Now again 1 goes to 1, again 1 goes to 4. So here is 4. Next we will start 2. So 2 goes to 5, and here 5 goes to 5, and 5 goes to 1. Next start from 3. So 3 goes to 3, 3 goes to 3, 3 goes to 3, 3 is as it is. So 4, 4 goes to 4, 4 goes to 4, 4 goes to 5. Next 5, 5 goes to 7, 7 goes to 8. Means we have to find chain such that 5 goes to 7. Check 7 value of 7, 7 goes to 8. So 5 goes to 7, 7 goes to 8, and 8 goes to 8. Now next 6, 6 goes to 6, 6 goes to 6, 6 goes to 6. Now 7, 7 goes to 2, 2 goes to 2, and 2 goes to again 2. Now 8 goes to 8, 8 goes to 7, and 7 goes to 7. So this is the product of this cycle. So this can be here these are all these are not disjoint cycles. So from this we have to find disjoint cycles. So the cycle is, what will we get from that? So 1 goes to 4, 4 goes to 5, 1 goes to 4, 4 goes to 5, 5 goes to 8, 5 goes to 8, 8 goes to 7, 7 goes to 2, 2 goes to 1. So 1 2. So 3 is fixed, 4 5, 6 is again fixed, 7 8. So this is single cycle of length 6. Now second, you can solve the same procedure. So here 1 3 2 7. So this cycle can be written in the permutation form, and this is 4 8 6 can be again written as permutation form, and taking the product of these two permutations or these two cycles you will get permutations. Now next we will see transpositions. So next definition, transposition. So what is meant by transposition? So if we have cycle, then every cycle of length 2 is called transposition. So a cycle of length 2, cycle of length 2 is called a transposition. Cycle of length 2 is called transposition, and a transposition leaves all elements. A transposition leaves all elements, is product of transpositions, is product of transpositions. A transposition leaves all elements is a product of transposition. Means if we have a cycle, then we convert it into product of two transposition. So let's see the corollary. Any permutation of a finite set of all set of at least two elements is product of transposition, is a product of transpositions. Any permutation of finite set of at least two elements is product of transposition. Means if we have a cycle which at least two elements can be written as product of transposition. So we will prove this. So proof of that. So a computation shows that. So now the computation shows that. So I will write here a single cycle having n elements. So I will write a1, a2, a3 up to so on an. So this is cycle of length n. So this cycle can be written as a into an. Sorry, a1 an. Next product a1. This previous of this is an minus 1. So this is a1 an minus 1. Next a1 an minus 2 up to so on. Last what will we get? a1 a3 a1 a3 a1 a2. So this is so a1 an minus 1 a1 an minus 2 up to so on a1 a3 a1 a2. These are transposition of cycles. So this can be written as a1 an minus 1 a1 an minus 2 up to so on a1 a3 a1 a2. So this is the product of transpositions. So thus any cycle is product of transpositions. So by theorem we have seen. So by theorem, so what is the statement of theorem? Every permutation of finite set is product of disjoint cycle. Every permutation of finite set is product of disjoint cycles. So every permutation can be written as product of disjoint cycle. This shows that any permutation of a finite set of at least two elements is a product of transpositions. Means we have a cycle whose length is n can be written as product of transpositions. So for example, if we have a cycle 1 3 5 6, then this can be written as 1 6 1 5 1 3. So this is product of transposition. So total how many transpositions are there? Total 3 transpositions, right? So next point is even and odd permutations. Even and odd permutations. So even and odd permutations. So what is mean by even permutation and what is mean by odd permutation? Now in a finite set A, if number of transposition is even, then the permutation is called even permutation, and if number of transpositions is odd, then permutation is called odd permutation. So we will see definition. Before that we will see note. So note that no permutation in Sn can be expressed no permutation in Sn can be expressed both as product of both as a product of an both as a product of an even number of transposition and as a product of as a product of an odd number of transpositions. Means here no permutation in Sn, means suppose you have Sn permutation, this cannot be expressed in both ways. Means if we have permutation which can be expressed which is either even permutation or which is either odd permutation, but which is not even and odd simultaneously. Means suppose we have permutation sigma, so 1 2 3 4, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 4 goes to 1. So this can be written as product of cycles. So 1 goes to 2, 2 goes to 3, 3 goes to 4, right? And this cycle can be written as product of this product of transposition. So transposition is 1 goes to 1 4, 1 3, 1 2. So it has only 3 transposition. So 3 transposition, so 3 is odd, means what we say that, so this is an odd transposition. Means permutation is either even or odd, but not both, means which is not even and odd both simultaneously. So which is at time even or odd. Now let's see the definition of even permutation and odd permutation. So definition first, even permutation. So a permutation of finite set, a permutation of finite set is even if it can be expressed as product of an even number of transpositions. Product of even number of transpositions. Means product of even number of transposition is called even permutation, and product of odd number of transposition is called odd permutation. So second is odd permutation. Odd permutation, this is even permutation. A permutation of finite set is odd if it can be expressed as product of odd number of transpositions. Means product of odd number of transposition is odd permutations. For example, we have the identity permutation. I in Sn for n greater than or equal to 2 is I is equal to 1 2 into 1 2. So this is product of 2 cycles. So this is, so each cycle has length 2, therefore this is product of even permutation, because here 1 2 means here n greater than or equal to we have to write 1 2. Suppose we have S3, so in S3, so total there are 3 symbols 1 2 3. So here 1 2 means 1 goes to 2 and 2 goes to 1, 3 is constant, and here 1 2 says 1 2 3, 1 goes to 2 and 2 goes to 1 and 3 is common. So product of these two is nothing but 1 2 3. So 1 goes to 2, 2 goes to 1. sorry, we'll start from here. 1, 1 goes to 2, 2 goes to 1. Now for 2, 2 goes to 1, 1 goes to 2. Now for 3, 3 goes to 3, 3 goes to 3. So 1 goes to 1, 2 goes to 3, sorry, 2 goes to 2, 3 goes to 3. Means what we say, this is an identity permutation, right? So every identity permutation for n greater than or equal to can be written like this: 1 2 into 1 2. This is product of two transposition. 2 is even transposition, means what, this is even permutation, right? Now for another example, so I equal to 1 2 into 1 2 has two transpositions. Two transpositions. Two transpositions means what we say, therefore identity permutation is so 2 is even, means identity permutation is even permutation, right? Now let's see another example. The permutation 1 4 5 6 into 2 1 5 belongs to S6. So which is, now to see this, so let's find out this is even or odd permutation. So we know that every cycle can be written as product of transpositions. So 1 4 5 6 into 2 1 5. So this cycle has 4 elements and this cycle has 3 elements. So from this cycle we have to find transpositions. So 1 6, next 1 5, next 1 4. So it has 3 transpositions, and for this, so 2 5 and 2 1. So how many total transpositions? So total there are 1 2 3 4 5. So total are 5 transpositions. So which has 5 transpositions, right? So 5 is odd, means what we say, so this is an odd permutation. This is an odd permutation, right? Now again find out. First 1 2 3 4 5 6 7 8. 1 goes to 8, 2 goes to 2, 6, 3 goes to 6, 4 goes to 3, 7 4 5 1. So this can be written as, so first find out cycle. So what is cycle? Product of cycle. So here 1 goes to 8, 8 goes to 1. So here 1 complete. Next 2 is fixed. 3 goes to 6, 6 goes to 4, 4 goes to 3. So here is complete. Now next 5, 5 goes to 7, 5 goes to 7, 7 goes to 5. So this is product of 3 disjoint cycles, right? Now to find out transpositions, so this can be written as 1 8. So transposition is product of disjoint product of disjoint cycles. So here I write 1 8. So this cycle can be written as product of transposition. So here I can write 3 4 3 6 and 5 7. So total there are how many transpositions? So total there are 4 transpositions. There are total 4 transpositions. 4 is even, so we say that it is even permutation. It is even permutation, right? So this is next example. Find out product of transpositions. So first find out product of disjoint cycles. So this can be written as, so 1 goes to 3, 3 goes to 4, 4 goes to 1. So 1 is in our set. So next we will start 2, 2 goes to 6, 6 goes to 2, so here is complete. Now next is here 1 2 3 4. Now we will start from 5. So 5 goes to 8, 8 goes to 7, and 7 move to again 5. So here is complete our product of disjoint cycle. Now to find out product of transposition, so then product of transposition is product of transpositions are, so this can be written as, so 1 goes to 4, 1 goes to 3. So this is cycle has two transposition. Now this is a single, so this is cycle of length 2, so which is single transposition. Now for this is cycle of length 3, so we have to find two transpositions. So 5 goes to 7 and 5 goes to 8. So total there are how many transpositions? 5. So there are 5 transpositions. Therefore what we say? Therefore it is odd permutation, right? So let's see. Note first, product of two even permutation is again even permutation. Second, product of two odd permutation is again even permutation. But product of even and odd permutation, product of even and odd permutation is odd permutation, which is very important. Means if we have two even permutation, then their product is again even permutation. And if we have two odd permutation means what? We have odd number of transposition, then the product of two odd permutation is again even permutation. But if one is even permutation and other is odd permutation, then their product is odd permutation. For example, here mu and here sigma, which is odd permutation, and here mu is again odd permutation, because this is product of single cycles whose length is 4. So this can be written as 1 3 1 4 1 2. So total here 3 cycles, and here again 3 transposition, means this is odd permutation, and here is one transposition, means which is again odd permutation. Then their products, so which belongs to what? S4. Then sigma can be written as 1 2 3 4. So total 4 symbol. 1 goes to 2, 1 goes to 2, 2 goes to 1, 3 and 4 are as it is, which belongs to S4. And mu can be written as, so here sigma mu are odd permutation, right? So here mu can be written as 1 2 3 4. So 1 goes to 2, 2 goes to 4, 4 goes to 3, 3 goes to, sorry, here 1 goes to 2, 2 goes to 4, 2 goes to 4, 4 goes to 3, 4 goes to 3, and 3 goes to 1. Then their product, so sigma into mu, which can be written as 1 2 3 4 2 1 3 4 into 1 2 3 4 2 4 1 3. So the product of these two, 1 2 3 4, 1 goes to 2, 2 goes to 1, 2 goes to 4, 4 goes to 4, 3 goes to 1, 1 goes to 2, and next 4 goes to 3, 3 goes to 3. After find out transposition, first find out cycle. So 1 goes to 1 is fixed. So 2 goes to 4, 2 goes to 4, 4 goes to what, 2 goes to 4, 4 goes to 3, and 3 goes to 2. So this is single cycle whose length is 2, whose length is 3. So this can be written as product of transposition. So it can be written as 2, 3 and 2, 4. So there are how many transposition? 2 transpositions. So having 2 transpositions, right? Therefore sigma into mu is, so sigma into mu has 2 transposition, means what? Sigma into mu is even permutation, right? So here sigma is odd permutation, mu is odd permutation, because here sigma has one transposition, so which is odd transposition, odd permutation, and mu has, so this mu is equal to 1, 2, 4, 3. It is again odd permutation, because this can be written as 1, 3, 1, 4, 1, 2. So total there are 3 transpositions, which is again odd transposition, and product of 2 odd transposition is again even permutation, right? Hence if we have 2 even permutation, then product is even. If we have 2 odd permutation, then product is even permutation. And if one permutation is even and one permutation is odd, then their product is always odd permutation. Now in next lecture we will see alternating group. Thank you.